Discovered by Professor Andre Geim at the University of Manchester in 2004, graphene is the thinnest and strongest material ever fabricated. While using Scotch tape to pull apart weakly bonded layers of graphite, Geim found under an electron microscope that a single layer of carbon atoms maintained cohesion despite being only one atom thick. Previously, it was postulated that it would be impossible to fabricate such a substance at room temperature because thermodynamics would cause the structure to lose cohesion and pull apart into microscopic balls. Surprisingly, not only did his lattice work of carbon atoms stay together, through additional study, it was found that graphene exhibited many unique properties never before demonstrated by another substance. Understanding the atomic structure and bonds of graphene can help us understand some additional properties of the material. Under an electron microscope, graphene appears as a hexagonal honeycomb mesh, which looks similar to a chain link fence. This organization enables graphene to be a two-dimensional surface that is both harder than diamond, and 150 times stronger than its equivalent weight in steel. If you placed a 4-kilogram baby, that's equal to 8 pounds 13 ounces, in a 1 square meter hammock of graphene, the baby would seem to be suspended in air invisibly, and the hammock would not break. Graphene's structure allows it to flex and stretch, and this adds to the overall strength and durability. Graphene's characteristics also enable it to blend well with other substances. In 2014, graphene was successfully reinforced with carbon nanotube to create an even stronger material. When combined with copper, it forms a material 500 times stronger than the original element. These properties could enable developers to fabricate stronger and lighter weight vehicles such as aircraft or fuel-efficient automobiles. Strength and durability are not the only unique characteristics exhibited by graphene. Graphene's latticework of carbon atoms each has 4 electrons in its outer shell, 3 of which fall in a plane, which is known as sp2 hybridization. The 4th electron can fall either above or below this plane, and because carbon atoms like to share electrons, this is known as a covalent bond, the 4th electron can move along the graphene structure at the speed of light. This makes graphene very good at conducting electricity. To be precise, graphene is 1,000 times more conductive than copper. Its intrinsic mobility, or how fast an electron can move through a metal semiconductor, is also 250 times that of silicon. Today, silicon is the premier material used throughout the world in the production of semiconductors for electronics. Moore's law states that the number of semiconductors, which are used in microchip fabrication, will double every 2 years. Basically, more semiconductors means more computing power. As semiconductors increase in number within silicon microprocessor chips, developers are forced to shrink their size. The downside of this shrinking is the impact on mobility, which decreases in silicon at a certain threshold. We are very near that threshold already, which is why graphene's size and mobility are so significant. Graphene has the potential to negate the current threshold limits of silicon-based microchips and enable developers to continue to shrink electronics and increase their computing power. Graphene is transparent and impermeable to both gas and liquids. Graphene is biodegradable and self-repairing. If carbon is introduced to damage graphene, the carbon molecules incorporate and seamlessly strengthen the original integrity of the latticework. Graphene is also very thermoconductive. The combination of these properties have the potential to push forward the development of future electronics that would be impossible with other modern materials. Imagine rolling up your laptop and sticking it in your pocket like you would a newspaper or a magazine. Bendable computer screens have already been developed using graphene, but further development will be necessary before mass production can begin. Combining graphene with other elements has enabled additional innovation. Although graphene is inherently impermeable, it's been theorized that nanoholes could be created within the latticework using hydroxy molecules, and the resulting structure could be used to desalinate water. Through reverse osmosis, graphene would filter water over 100 times more efficiently and much less expensively than any other process being used today. The composite graphene oxide will flake into polymers that show enhanced photoconducting properties. These could be incorporated into solar cells that would have the ability to capture every wavelength of light. This would be much more efficient than current materials, which are limited in their ability to capture different light wavelengths. Speaking of energy capture, another innovation that graphene has the potential to offer relates to batteries. These typically operate by using toxic chemical reactions to produce energy, but the reactions are inefficient, they generate heat, they lose capacity over time, and they are slow to charge. Graphene supercapacitors are different. Instead of using chemicals, these supercapacitors could simply store the electricity necessary to operate a device. They would have a greater capacity, and they could charge in seconds instead of minutes or hours. To many, graphene appears to be the new miracle substance of the 21st century. In 2010, Geim and his research colleague Konstantin Novoselov received the Nobel Prize in Physics as a result of this unprecedented discovery. Since 2004, progress continues to be made in developing new methods of utilizing this amazing substance. To date, however, graphene is only being used on a large scale in tennis rackets and ink. A major limit of graphene is scientists' inability to synthesize sufficient quantities to make large-scale production possible. While developers continue to work away at this hurdle, both the scientific and business community are hopeful that graphene's unique properties can be incorporated into
Graphene is often described as a one-atom thick layer of carbon with strict geometric structure and some extraordinary properties. It is 100 times stronger than steel of the same thickness, conducts heat and electricity efficiently, and is nearly transparent.
This material has so many potential applications that you don't know where to start to look at the beginning.
Dan Schaefer, Vice President of Vorbeck Materials, says pure graphene is hard to manufacture, but graphene of lesser purity can be made, and it still keeps many of its features.
So, cannot be perfect, will not be 100% single sheets, but our production is providing more than 80% that it's amazing purity actually.
If you mix graphene into a paint, you can print flexible, electrically conductive components, such as antennas for radio frequency identification circuits. The manager of the product's development team, Louise Brooks, says graphene is also suitable for wearable electronic garments.
You can throw it in the washing machine, you can throw it in the dryer, and it'll survive those cycles, but it'll also survive sort of normal wear and tear from just running around as you wear your clothes.
There's another special application for the new material, extra-sensitive microphones. Engineer Ray Sauro says this graphene membrane, less than 1 micron thick, can pick up vibrations no other membrane can.
It has a working range of less than 1 hertz to 200,000 hertz. The human ear, for example, can hear from about 15 hertz to 20,000 hertz, so way beyond anything you can hear.
The sound is picked up as a change of light reflected off the vibrating graphene membrane, so there's no radio or magnetic interference. Sauro says graphene membranes can withstand vibrations and heat and are cheap to manufacture, so he envisions applications in the automotive industry for monitoring the health of car engines. The cost, he says, would not be more than $300. George Putich, VOA News, Washington.